You ever run a comb through your hair on a dry day and suddenly it's all standing on end? Or, when you reach for a metal doorknob and get that surprising little zap. It feels kind of like everyday magic, right? Well, it turns out it's not magic at all. It's science. And today, we're going to pull back the curtain on that strange phenomenon, static electricity.
So this is our big mystery for the day. How in the world does a simple plastic comb suddenly get this invisible superpower to just pull little bits of paper toward it? Stick with me, because by the end of this, not only will you know the answer, you'll see how this exact same principle is behind some of the most incredible technology we use every single day.
All right, to solve this puzzle, we need to meet the main suspect. The thing responsible for all this invisible action is something called electric charge. And the craziest part? It's everywhere, in everything, all the time.
So what even is it? Well, electric charge is just a basic property of matter, just like mass. Every single atom is built from particles that have this charge. And it basically comes in two distinct flavors. You've got your positive and you've got your negative. Sounds simple enough, right? But the real magic, the real action happens when we see how these two flavors interact with each other.
And here it is. This is the one, simple, unbreakable rule of the entire electrical world. Opposites attract and likes repel. It's that simple. A positive and a negative charge will always be drawn to each other, but two positives or two negatives, they'll always push each other away. If you can get this one rule down, you've basically unlocked the secret to everything we're about to talk about.
Okay, so you might be wondering, if everything has these charges, why isn't the whole world just constantly sticking together and flying apart? Well, the answer is balance. See, most of the time, things are electrically neutral. They've got an equal amount of positive and negative. To get those cool static effects, we've got to mess with that balance. We have to get the charges moving. Let's look at how that's done.
Now, here's a crucial point. Not all materials treat charge the same way. Some things, we call them conductors, think of any metal, are like wide open superhighways for charges. The charges can just zoom around freely. But other materials, called insulators, like say the plastic in our comb, they're the complete opposite. They're more like a massive traffic jam. Charges can get stuck on them, but they can't move around or leave easily. And this one difference is the absolute key to static electricity.
So how do we get those charges moving in the first place? Well, there are three main ways. You can use direct contact, which is called conduction. You can even charge something without touching it at all. That's called induction. But for our comb mystery, the answer is number one, friction. When you rub that plastic comb, an insulator, remember, through your hair, you are literally scraping tiny negative charges, called electrons, right off your hair and onto the comb.
Okay, so we've pretty much cracked the case of the comb. But this isn't just some neat party trick, This simple interaction is actually governed by some really deep, universal laws of physics. So let's zoom out for a second and look at the fundamental rules of the game. These three properties are basically the bedrock of all electrostatics. Additivity just means you can add them up. Simple as that. Conservation is a huge one. It means you can't just create charge out of thin air. You can only move it around, just like we did from the hair to the comb. And quantization, well, that one is seriously fascinating. What quantization means is that charge isn't some smooth, continuous liquid. No, it comes in tiny, indivisible little packets. The smallest possible piece of charge you can ever have has this ridiculously small value. Every single bit of charge in the entire universe is a whole number multiple of this one fundamental unit. You can have one, or two, or a million of them, but you can never ever have half a charge. And what's really amazing is that we can actually calculate the exact strength of that push or pull. There's a rule called Coulomb's law that lets us do it. Now, you don't need to memorize the math, just get the two big ideas. The more charge you have, the stronger the force. And the more distance between the charges, the way weaker the force gets. It drops off incredibly fast as things move apart.
So how does a charge all the way over here know that another charge is over there? I mean, they don't have eyes. They interact through this invisible field of influence that surrounds them. It's time to talk about the electric field.
Probably the easiest way to think about an electric field is like the aura of a charge. It's this invisible zone of influence that extends out in all directions. Any other charge that happens to wander into this zone is going to feel a force. So, our negatively charged comb creates its own electric field, and it's this invisible field that reaches out and actually grabs onto those little pieces of paper.
Now, since we can't actually see these fields, physicists came up with a really clever way to map them out using what they call field lines. You can think of them like currents flowing in a river. The lines always point away from positive charges and toward negative ones. And here's the cool part.
Where the lines are packed really tightly together, the field is super strong. Where they spread out, the field and the force is much weaker.
All right, so we've gone from a simple plastic comb all the way to fundamental laws and invisible fields. But why does any of this matter? Well, because once we understood these rules, we learned how to control them. And that changed everything.
And this is where it all comes together. That exact same principle that makes paper stick to a comb, that's what makes the toner powder stick to the paper in your photocopier or laser printer. It's how we use giant electrostatic plates to pull soot and pollution out of factory smokestacks to keep our air clean. It's the core idea behind capacitors, which are absolutely essential components in pretty much every electronic device you own. This stuff isn't just a classroom mystery, it is literally the engine of modern technology.
And that's really the key takeaway here. The next time you feel that little shock from a doorknob or you see a balloon stick to a wall, don't just brush it off. It's not some trivial weird thing. It's you having a direct personal encounter with one of the fundamental forces that built the universe. Understanding that tiny little spark is the very first step to understanding the incredible technology that powers our entire world.
From a simple, everyday observation to world-changing applications, the story of static electricity is just a perfect example of how scientific curiosity works. It really makes you wonder, doesn't it? Now that we've mastered this fundamental force, what other everyday mysteries are just sitting there, waiting for us to understand them, harness them, and use them to power our future?